This video is 2.1a, Power and Radical Functions. By the end of this video, you should be able to graph and, more importantly, analyze different types of power functions. When we were discussing parent functions in the first unit in 1.6, several of the functions that we actually have already looked at are pretty much classified as power functions. A power function is any function that takes the form of f of x is equal to some constant x to some power n, where a and n are both non-zero constants. Power function is also a type of monomial function. So if you remember what monomial means, it really just means that it has one term. And so when we analyze these monomial functions, we have one of four possibilities. So let's pause for a minute and let's get the first set in. So if f is a power function, f of x is equal to x to the n, where n is a positive integer, we can either have the exponent be odd or the exponent will either be even, which is going to be our first case here, and then what changes is whether or not the constant in front, the a, is positive or negative. So why don't we pause the video and let's get this important information in our notes, because these are things that are common for pretty much all power functions that take this form. The other possibility is that the exponent is odd in both cases, but then what happens is that we also do the same thing where a can be positive or negative, and then we'll find that we'll have these possible behaviors. So let's put these behaviors in. Okay, let's try an example with it. So using your graphing calculator, graph the following power function and describe the domain, range, intercepts, and behavior, continuity, and where the function is increasing and decreasing. So if we look at this first example, it's f of x is equal to 1/2 x squared. So a couple of things that we should note right off the bat is that the value here is positive, and that my exponent is even. So if we look at the graph of the function, that's what it looks like. And so what I can do now is, just looking at this function, I can describe the domain and the range and all of the information that I need. So for example, I know that the domain of this function is going to be all real numbers, so it'll be from negative infinity to positive infinity. And I look at the range of this, and I want to get the range, so I find the lowest y value, which will be from 0. And it goes up forever, so it will be positive infinity. The x-intercepts we're going to write as coordinates, so it looks like it comes down here. And the x and y intercept are both going to be at 0, so this is going to be at 0, 0, and 0, 0. And if you remember, if we're talking about end behavior, we're writing it as two limits. So we're going to write it as the limit as x goes to negative infinity of f of x. And so that's as we start from the center and we go out this way, and we'll see that it goes up to positive infinity. And then the limit as x goes to positive infinity of f of x. If we start at the center of the graph and we start going out this way, we'll see that the behaviors of the y values also increase up to positive infinity. The increasing and decreasing behavior, we just look at the graph, and now we start reading from left to right. And from the left, as we start moving from the left, we see that the y values are decreasing until they hit the origin. So I can say that this graph is decreasing from negative infinity to 0, and then it's increasing from 0 to positive infinity. And this matches up pretty much exactly with the table that we just got, that we just filled out for a positive a value and an even integer. Try one more. So I have f of x is equal to negative x to the 7th. This is what my graph looks like. It's not a great picture, but we can get pretty much all of the information we need out of it. Since a is negative and the exponent is odd, we can determine the domain, the range, and we can use all of the things that we got before. So the domain of this function will be from negative infinity to positive infinity. The range will be from negative infinity to positive infinity. The x and y intercepts are still 0, so it's going to be 0, 0, and 0, 0. The end behavior we write as two limits. So the limit as x goes to negative infinity of f of x. So I start at the center of the graph, and I see that the graph is increasing to negative infinity here, or positive infinity, sorry. So it goes to positive infinity. And then the limit as x goes to positive infinity of f of x. And I start at the center of the graph, and I start moving to the right, and I see that the y values are going to negative infinity. So let's move this out of the way. This is going to negative infinity. Continuity, which I forgot to do in the one before, the continuity interval is the same as the domain. So the domain or the continuity interval is going to be negative infinity to infinity. This graph is never increasing. It is only ever decreasing, so it's only decreasing, it's decreasing from negative infinity to positive infinity. We can also do this with negative exponents. So if you recall that f of x is equal to 1 over x equals x to the negative 1 is undefined at x equals 0. So essentially negative exponents turn into functions, turn functions into reciprocal functions. So even if we were to do this graphical analysis, we can still do it with negative exponents. So if I say, well, this is f of x is equal to 3x to the negative second power, that's really the same thing as saying 3 over x squared. And that's going to give us some asymptotes. But what we can do is that we can analyze the function, and we can just see that pretty much x can equal 0, and that's going to affect my domain, and it's going to affect my continuity, but it's really not going to affect too much else. It's also going to affect my intercepts. But so the domain of this function would be from negative infinity to 0, union 0 to infinity. The range, since this is essentially an even number, is still going to work out to be the same as it was before when the exponent was even, and it'll go from 0 to infinity. There are no x-intercepts or y-intercepts because of the asymptote happening at the center of the graph, so we can just write not applicable, or NA, and NA. End behavior is going to be switched a little bit. So if we look at it, the limit as x goes to negative infinity of f of x, well, if I just look at my graph and I start from the center and I work outwards to the left, I see that my values start up really high and then they start getting really low, and they're approaching pretty much the x-axis. So it's actually going to approach 0. And it's going to do the same thing on the other side. So that means that the limit as x goes to positive infinity of f of x is also going to go to 0. We said that the continuity and the domain are going to be the same intervals, so the continuity matches the domain, which is going to be from negative infinity to 0, union 0 to infinity. Increasing and decreasing, well, this function will be increasing if we look at the left side of the graph. It starts off from negative infinity and it starts approaching the y-axis and the graph starts to increase up. So I know that the graph will increase from negative infinity to 0. And then once it jumps over the asymptote, it's going to start decreasing quite rapidly. So it's going to be from 0 to infinity is going to be decreasing. Try one more. So we have f is equal to negative 3/4 x to the negative 8th. So let's just take a look at the graph of it, and let's analyze. Okay, the domain is still going to be the same as it was before, so we know that x can equal 0. So you'll have you'll have from negative infinity to 0, union 0 to infinity. The range is going to cover pretty much everything, except it's going to have a horizontal asymptote here. It's kind of hard to see, but the range on this function will actually pretty much mirror the domain. It'll be from negative infinity to 0, union 0 to infinity. There's a horizontal asymptote happening right here. There are no x and y intercepts again. And end behavior is pretty much going to mirror the same one as it was before. So it'll be the limit as x goes to negative infinity of f of x equals 0. And the limit as x goes to positive infinity of f of x is also 0. Continuity is going to be the same as the domain. Negative infinity to 0, union 0 to infinity. The function is increasing from negative infinity to 0, and it's never actually decreasing, so it's also decreasing from 0 to infinity, or increasing from 0 to infinity. So union 0 to infinity, and it is never decreasing. So we've talked about positive exponents, we've talked about negative exponents. The last thing that we have to talk about in terms of a power function is whether or not we have a rational exponent. So rational exponents take a normal power function and transform it into a root function. So essentially, when we say that if we have x is equal to, or f of x is x to the 5 halves, what this is really saying is that we want to say that we're going to turn it into the square root of x to the 5th. Okay, and if we graph that function, that's what it looks like. And we can take a look at it and we can start analyzing it. So I know that looking at it, the domain will go from 0 to infinity. The range will go from 0 to infinity. The intercepts will go from, will be at 0, 0 and 0, 0. This function actually has no right end behavior since it stops right here. So we can only talk about it, it has no left end behavior. We can only talk about it in terms of its right end behavior. And so I can only say that the limit as x approaches infinity of f of x is equal to positive infinity. Continuity will be the same as the domain interval, so it'll be 0 to infinity. This function is only ever increasing from 0 to infinity, and it's never decreasing. Okay. I want you to work on the following pages, and this will be homework that I will check on Monday. You'll have another assignment to do tomorrow.